Okay, nice. We're inside there. We fixed that. All right, so good. We could, let's go back and sleep now. All right, so good. Let's continue. Y'all got it? A plus B to the power of n. Anybody got it? Yeah? Yeah? Okay, nice. So that'll be a to the power of 5 plus 5c1, a to the power of 4, a to the power of 4, b to the power of 1, plus 5c2, a to the power of 3, b2, 5, 3, a to the power of 2, b cubed, 5, 4, ab 4, 5, 5, b to the power of 5, right? Check it out and see. Right? So this is what it will look like, right? Before we go into the Morse theorem, I just want to make sure that you can handle this. And I will do the first one for you, right? Everybody okay with binomial expansion? Yeah, everybody can follow the rule, right? All right, so what you're going to see now is I am going to ask you to expand cos theta plus I sine theta to some power, right? So let's say to the power of 3. So let's make it easy, right? Some people find it long when you have to write cos and sine. So an alternate is this. If you don't like it, well, you don't have to use it, right? Instead of writing cos, write C. Instead of writing sine, write S. And then we're going to try to expand this, right? This is your A, this is your B. This whole thing is a B, right? Together with the sine, right? And of course, this is your N. So I'm going to try to show you how you can do that expansion, right? So that'll be C cubed. I am using the C plus IS, right? That'll be C cubed plus 3C1, C squared, IS to the power of 1, right? That's important. The I goes with the S, right? Plus 3C2, C squared, IS squared. Sorry, there should be 1. Plus 3C3, IS to the power of 3. So what you're going to get here is this. You're going to get C cubed plus 3C squared by IS. 3C2, that's 3C. Here you will get I squared, S squared. 3C3, that's 1. So that'll be 1 by I cubed, S cubed. All right? So here you will get C cubed plus 3C squared, SI. The reason I put the I on the end is I want you to identify that this is an imaginary term. So within the whole expansion, that part is an imaginary part because it has an I, right? I squared, we know I squared is -1, so you get to use it here, William, right? All the I squared and Q and I important thing, you get to use it here, right? So we're going to take off I squared, which is -1, and you will end up with -3C S squared. Next one is I cubed. We know that I cubed here is -I. So we'll be left with minus S cubed by I. Okay? And we can now replace everything, and you're going to get cos cubed theta plus 3 cos squared theta sine theta by I minus 3 cos theta sine squared theta minus sine cube theta by I. Right? And that's it. That's the way you expand it. And then we're gonna take the real parts, and then we're gonna take the imaginary parts. And I'll show you what will happen after. Okay, so that's all we're going into now. Once you know the binomial expansion formula, right? Once you know that binomial expansion formula, all we're going to do is just expand and take the real and imaginary parts, right? The theorem now, what De Morve's theorem is going to allow us to do is going to allow us to create trig identities. Okay. Right? Any question with this sign and cos? Right. Anybody writing? I can turn. Turning, right? Anybody writing there? All right, so I'm going to turn, right? All right, so now it's time for De Morve's theorem. It's M-O, think. All right, I think that's it there. It's I plus IV. All right, so De Morve's theorem, right? We kind of showed it. If you check back about 2 or 3 pages, we kind of showed this theorem already. And that was when we were doing the Z to the N and thing, right? I think I showed you all the theorem. But the De Moivre theorem basically states this, right? Right, it states that if we have cosine theta plus I sine theta to the power of n, it is equivalent to, right? All we have to do is just take the n and bring the n in front here, right? And I showed you where that came from in one of the earlier slides, right? So that'll be cos n theta plus I sine n theta, right? So if you have cos theta plus I sine theta to the n, is the same as cos n theta plus I sine theta, right? So a quick example, right? Cosine theta plus I sine theta all to the power of 4 is equivalent to cosine 4 theta plus I sine 4 theta. That's it. That's the rule. Now here's where we're going to use the binomial, right? If you want to find this, all you have to do is expand this and take out the real part. If you want to find identity for sine 4 theta, all you have to do is expand and take out the imaginary part. So this here is the real part of the expansion. Right, that's the real part of this expansion, right? And this here is the imaginary part, right, of the expansion. So as I was showing you before, you're going to have to expand it, right? So for example, if I say, well, use De Moivre's theorem to find cos 4 theta, then this is what you have to do, expand and work it out. All right, screenshots or write it down quick. All right, so let's just try one. Let's see, let's see here if we could use De Moivre's theorem to find cos. Let me see. We did 3 already. We did 3, so let's do 4. Cos 4 theta. All right. So here's what we have. We have cos theta plus I sine theta to the power of 4 is equal to cos 4 theta plus I sine 4 theta. Right. And what do we need to get cos 4 theta? We need the real part, right? So we're trying to get the real part of the expansion. So we're going to expand it. For space, I am going to use C and S. If you all do like it, just write it out, right? Right, but I am going to use C and S. So that will be C plus IS to the power of 4. Right? That'll be C to the power of 4 plus 4C1 C cube IS to the power of 1 plus 4C2 C squared IS squared plus 4C3 C by IS cubed plus 4C4 by IS to the power of 4. Right? 4C1 is what? 4? That's 4, right? For sure that's 4. No. So that's C cube SI. Right? I squared, so you'll get minus. What is 4C2 again? That's 6, I think. Yeah, that's 6. So that's 6 C squared S squared plus 4C4, that's 4. Right? But that'll be minus C S cube I plus I to the 4th is positive 1. So that'll be S to the 4th. Okay, so I just going to separate the real and the imaginary. So this is C4 minus 6C squared S squared plus S4 plus 4C cube SI minus 4CS cube I. Right? So this here is the real part. Right? That's the real part there. So therefore, cosine 4 theta is equal to cos to the 4 theta minus 6 cos squared theta sine squared theta plus sine to the 4th theta. Right, so that last line there is your identity for cos 4 theta. Yeah? Copy it down. Any questions? Everybody okay there? Everybody finished, right? All right. That's assuming, huh? Okay, so that's try this one here. Number 2, again, use De Mor's theorem. Right, start with something easy, right? To find sine 3 theta, but I'm gonna add a little twist to it. I want you to find sine 3 theta in terms of sine theta only. So you're not allowed to have cos like here. You see like how we had sine and thing, you want to get all sine, all cos. Right? Try that, please. In this case, in the one I gave you, I want all sine. Try the expansion easy because we did it already, right? All right, that's not it finished. Just let me know you're finished, right? Don't forget to message when you finish. Thanks. Excuse. All right, so you should at least have this part, right? So you have cos theta plus I sine theta all cubed. I think we did this part already, right? All right, we did it earlier up here. All right, somewhere up here we did it. Yeah, look at it. All right. I don't think I separated. All right. So we got cos cube theta plus 3 cos squared theta sine theta I minus 3 cos theta sine squared theta minus sine cube theta I. Right? Right. Remember, if we buy De Mor's theorem, cos theta I sine theta cube is equal to cos 3 theta plus I sine 3 theta. So since we want to get sine 3 theta, we want the imaginary part. Right? If you look up here, the imaginary part is here and here. So therefore, sine 3 theta, right, is equal to 3 cos squared theta sine theta minus sine cube theta. Okay, but the question asks in terms of sine alone. So going back to an easy identity that we should remember, cos squared theta is 1 minus sine squared theta. Right, so it means that sine 3 theta is equal to 3 open brackets 1 minus sine squared theta by sine theta minus sine cube theta. So we'll be left with 3 minus 3 sine. Let me just expand this out one time, right? 3 sine theta minus 3 sine cube theta minus sine cube theta. So that will be 3 sine theta minus 4 sine cube theta. Three sine theta minus 4 sine cube theta. Anybody got that for sine 3 theta? Yeah. All right. So that's in terms of sine only. All right, nice. So that is your De Mor's theorem. Let's do a past paper and let's finish up on complex numbers, right? And the space. All right. Anybody writing? Anybody writing? Taking this off, right? So we're going to attempt. I'm gonna see if I get a good copy first. $17.60. I think I have a good copy here. Yes. All right. So we're going to attempt 2018. Taking this off, right? Let's try 2018. All right, so we go in here first. All right, let's prove that. That is 5 marks. Right, 5 marks, and then we're gonna do this thing here, and then we're gonna do this thing here. Wait, did I do this already? I hope not. All right, so start here. Use the Morse theorem, and when you finish, correct it, then we go to the next one. Wait, this is 2018. Shops, I get them wrong one. Supposed to give them 2019. All right, that could work. What number? It is number 1. Number 1, part C. Wait, I gave you the wrong one, but that could still work. 19 and 18 is similar, just changing numbers. But do this one first. All right, do this, and let's do the last part. All right, try that for me. Cheetah, all again, through there. Cheetah. Cheetah, are you okay there? William, you didn't question, right? Open a message in nobody, yeah? With heart something again. All right, nice. Do this for me, and then we have. All right, I just going to send a couple of years in the group, right? So you say I have them for those who are going a little faster. You're done? The 2019 version of this, all they ask for is in terms of sign alone. Finish, right? Kill and finish. So I'll start in there. All right. So again, I don't really have all the space in the world. So I hope this work. Hold on, I'm gonna just like this. This class feeling like it'll be a whole day class. So let us see. So as I said, De Morve's theorem will. Right, sometimes this has happened. Right, working on cos theta plus I sine, and I not 35 is equal to cos 5 theta plus I sine 5 theta. All right, so because they want sine, what we'll do is we'll take the real part, the imaginary part. Right, I wonder if this will help. So, what will the expansion be? It'll be, all right, would I be able to fit it? But let's see. Cos 5 theta plus 5c1 cos 34 theta by I sine theta. Then looking so, huh? Right, I will go back and use C and S, right? So that'll be C5 plus 5C1, C4, IS to the 1 plus 5C2, C cube, IS squared plus 5C3, C squared, IS cube, 5C4, C, IS to the 4th, 5C5, IS to the 5. Right, so here you will get C5 plus 5C4 S to the I, S by I, plus 5C2, that's 10 I. So that'll be 10 C cube S squared I squared plus 10 C squared S cube I cube, right? Plus 5C, right? So that'll be 5C S to the 4th I to the 4th plus S to the 5 I to the 5. Nice. Then you make a little substitutions. So that'll be C5 plus 5C4 SI. I squared is minus 1, so this becomes minus 10 C cube S squared. I cube is minus I, so that'll be minus 10 C squared S cube I. C to the 4th is positive 1, so that's 5C S4. And I to the 5, if you remember, I to the 5 is just I, positive I. Right, so that'll be S5I. Okay. So let us see how we will do this. I'll take out the imaginary part one time. Right? The imaginary part will be here, here, and here. Real easy, right? So that'll be sine 5 theta is equal to, I'll convert back to cos and sine. So that'll be 5 cos to the 4 theta sine theta minus 10 cos squared theta sine cube theta plus sine to the 5 theta. That's it there. Right, sine 5 theta minus 10 cos squared sine cube plus 5 cos to the 4th, right? They just rearrange it differently. All right. Any questions here? Right, and again, if they ask in terms of sine only, then you're going to have to remove this and this. As if they ask in terms of sine, right? All right, next part. Anybody can check and see if I did this one already. 1 minus I. In polar, in exponential form, and then you had to I 1 minus I to the power 9. Check and see if that's the one I did yesterday. Wednesday. Yeah, okay. That's the one I did. All right. All right, but when you all finish, copy this down. I know I did this question on Wednesday, but I didn't give you in this form. So we could do that for me now, please. 1 minus I to the 9. I think we found the modulus and the argument. I want you to see if we could show that. Right, see if we can find the modulus and the argument. Anybody could tell me about what the modulus was? What was the modulus of 1 minus I? Well, all right, that's easy, right? That was with 2. Anybody can tell me what we got the argument to be? What was the argument of 1 minus I? That's 4th quadrant, pi on 4, I think. Negative pi on 4, thanks. Negative pi on 4. Good. So now, 1 minus I to the power of 9, right? 1 minus I to the power of 9, that will be one the modulus and argument of that. Right, the modulus, I think we worked out the modulus, that would have been the square root of 2 to the power of 9, or 2 to the 9 on 2. Nice. And we got the argument of that would have been minus 9 pi on 4, but I was out of the range. So we got what? What was the value in the range? All right, minus pi on 4. Nice, so we got to go. So we have the modulus here and we have the argument. I want you to try to figure out now how you're going to show that. If you get it, just message prove on of QED. How you're going to show that 1 minus I to the 9 is the same as 16 by 1 minus I. Try that, please. Nice. One person get it. I'll give you a few minutes again. All right, let's check it out. All right, what you got? What did you get? So, to get this out, one of the best forms to use here, instead of the Cartesian form, is to write the polar form, right? So the best thing to do is to take this and put it in the polar form. If you put it in the polar form to look like this, it will be root 2 to the 9, well, 9 on 2. 2 to the 9 on 2, open brackets, cosine negative pi on 4 minus pi, negative pi on 4, I sine negative pi on 4. Now, what we could do is we could actually go to the calculator and work that out, right? If you work out cos negative pi on 2, how much you'll get? Straight in the calculator. Was cos negative pi on 2? My pi on 4, sorry. All right, that value is root 2 on 2. All right, and you do the same thing there for sine. All right, you're supposed to get negative now, right? So you put the value straight in the calculator. And here you will get minus root 2 on 2. All right. So once you have that, now we could try to multiply it out, right? Or we could factor out negative root 2 on 2. So you will get 2 to the 9 on 2 multiplied by root 2 on 2, and you have your 1 minus I here. Okay, you have your 1 minus I on the inside. So the inside good. All we have to do is just multiply out the outside. Okay, and when you multiply that, when you multiply root 2 on 2 by 9 to the half, you will end up with 2 to the power of 4, I think. Yeah, 4, 8 on 2 by 1 minus I. And that's it there. 16 by 1 minus I. Right? So in order to figure it out, you had to put it in the polar form. And then from the polar form, you could work out, you could go from the polar back to the Cartesian form right there. Yeah? Say that, Kyle? Yeah, you okay with that? All right, nice. Right, one more, and then we will take a look at the last thing, right? Right, so today we'll finish up complex numbers. Any questions here? Anybody? Rana, any questions? Shabara? All right, nice. Let us do now 19, right? We're leaving out the first part of 19, right? Right, that's what we're doing next, differentiation, next week. Right, we're leaving out this De Moivre's theorem, right? The same thing as 5 theta, but all they want is sine alone. Right, so you're just basically using what you had from before and replace the cos. All right, so you could always try that. We're focusing on part C. Right, complex number and then show this. I just leaving this part up alone, right? So we did one just like this already. All I want you to do is see if we can prove the decimal. Just like the one that we did, 1 minus I to the power 9. All right, try this, please. Right, once you get it, just message shown, right? Or QED. Message QED. Right, and then we have thing to do. Right, who got the last one again? Take your time with this one. Just the numbers change, right? And remember to find the argument within the range, right? Any more? We have one from Chelsea here. Any more? Kilon, Rahul? All right, 2. Shavish. Almost, okay. Go ahead. Go ahead. I just going to check out the first part, right? I am from outer space. All right, let's get the modulus. I just call it z 1 minus root 3i, right? So the modulus of z, that will be the square root of minus 1 squared plus root 3 squared. 3 and 1 is 4, so that's 2. Argument of z, right? That will be tan inverse root 3 over minus 1, right? Which quadrant is that? Negative, positive, second quadrant, or shucks. Add pi, right? How much you all got there? What was the argument? My calculator is in radians still. Ah, 2 pi on 3. Nice, thanks. 2 pi on 3. Good. And now they want so z to the power of 7, right? You want the modulus of that. That'll be 2 to the 7. So that's nice and easy there. And then they want argument now. Argument of z to the 7. That will be 7 by 2 pi on 3. Right? So that's 14 pi on 3. Right? So that's about how much? 4 and 2/3. So that's 4 and 2/3 pi. Right? Yeah, 4 by 3 is, yep, correct. Right, but not in the range, right? So this is not in the range. So I need to get the equivalent, so I'll do the little cycle thing. Positive, so I'll go in anti-clockwise. 4 pi, right? So 4 and 2/3 pi. So this is 1 pi, 2 pi, 3 pi, 4 pi, and 2/3 pi right here. So same place, 2 pi on 3. So that makes it easy, right? 2 pi on 3. Right? So remember I told you that this is the part that'll be accepted, right? 2 pi on 3. Right? So what does that mean? It means that negative 1 plus root 3i to the 7 in polar form will be 2 to the 7 by cosine 2 pi on 3 plus I sine 2 pi on 3. Okay, go take calculator, you work out your cos 2 pi on 3. Right, that should be, I got negative a half, right? Negative a half. And here should be something similar. That'll be minus root 3 on 2. I'm from outer space. Right, yeah, correct. Right, so I could factor out a half. So that's 2 to the 7 over a half by minus 1 plus root 3i. This will be 2 to the 6. 2 to the 6 is 64. So that's 64 minus 1 plus root 3i. Okay, nice. So we have it there, QED. Okay, so that's the first part of complex numbers. The next thing that we have to do is to do loci, right? Copy it down. Any questions on this? Right, the hardest thing, or the one thing that we have to remember is this. We have to remember to do this. The only good thing, good thing is that if you take this value here, any one of those and put it in here, you will still get this line. So you'll still be able to do the proof, but you will not get the argument part right. Right? You will not get the argument part right. Right, Nathaniel? It's the same thing that we did yesterday, right? 7 by 2 pi is 14 pi on 3, but that is not in the range, right? That's not in the range negative pi to pi. So what you have to do is to find the equivalent. So 14 pi on 3 is the same as 4 and 2/3 pi. So we're doing the quadrant technique, right? We're going to find the equivalent of 4 and 2/3. So this is 1 pi, 2 pi, 3 pi, 4 pi. 4 and 2/3 pi is like right here. So it means that the accepted parts will be here to here. That will be the argument within the range, right? And that value there is 2 pi on 3. All the others, the little circles there, that's just to give you an idea of or to help you find the equivalent of 4 and 2/3 pi. That's okay. If you look back at yesterday, we did a couple examples. I mean, Wednesday we did a few examples as well. Right, so you have to find the equivalent within the range. So you do the cycle, so you kind of basically canceling off, right? What not necessary. So like the 4 pi, you just cancel that 4 pi off in the end. It's work out easy when it's even, like 2 pi and 3 pi and 2 pi and 4 pi and 6 pi and things, those easy. When it's like 3 pi, it's be a little bit different, right? You'll have to cut off, right? Let's just say it was 3 and 2/3 pi. Right? What you will have to do in those cases is this: 1 pi, 2 pi, 3 pi, and your 2/3 pi will be like here. So the answer that you are going to take, you have two options. You could take your answer here, but that'll be out of the range. So you'll have to take your answer here. So your answer will be pi minus 2 pi on 3. So that'll be negative. Well, it'll be pi on 3, but it has to be negative. Hold on, let me just make sure I subtract. Yeah, 2 pi on 3. Well, 2 pi on 3. Oh, I see what 2 pi on 3 quite here. That's 2/3 pi. Let me just fix it. I think I drew it bad in the last one too. I should have stopped quite here. Right? 2/3 pi will be on that side. Same answer. I just drew the diagram a little bad. Right? So like here, if it's 3 pi, it will be 1, 2, 3. That's 3 pi, and 2/3 is quite down here. Right? So I should have stopped there. So the answer that you will use is right here. Right? Negative pi on 3. That's okay? Everybody okay with that conclusion? Chelsea, you okay? Nabil, you're okay with those conversions? All right. Okay, nice. What to do, boy? Give me a break now. You want to break now, or you want to go straight to Lucas? Loci. Want to break now? All right. Okay, all right. Well, take a break because we have one more thing to do in complex numbers. And we'll just introduce it, right? So sometimes you will see the modulus of z minus 2 is equal to 5. And they want you to represent or give the locus of that. So we have to work out what equation this represents. So it will be like a circle or a straight line, right? Or a curve, right? So we are going to learn to figure out what the loci is. Okay, I'll show you the long way, and then I'll show you a formula for you to use just to recognize it and sketch it. Okay, all right, take a little break. You can have your lunch. I'll give you 8 and hopefully lunch ready. For some of them, breakfast, so breakfast should be ready. Take like 18 minutes. Take like a 20 minutes, right? Take like a little 20 minutes, have your lunch, and then we come back. Right? So we will start around 12:15 or so. Right? 12:15, we will start back. Okay? It's up to you. You all can stay logged in, right? Right? So we will start back at 12:15. Right. Ready? Here we are, extra 10 there. You all there? Everybody there? All right. That's enough years there. I'll go with that. Okay, so last thing we have to do is something called the loci, right? I will give you a few of them. As I said, I'll give you the short version and I will give you the slightly longer version, right? I'll start with the long version to explain where everything comes from, right? So hold on. Da, da, da. Da, da, da. Da, da, da. Da, da, da. Shucks, I didn't take the rule. All right, so good. So just a quick review. Remember that the locus of a point is to set up all the points, in this case, in a complex plane, right? That satisfies the given functions or conditions I give you, right? So basically, if I tell you, just like what we had before, it's always the same distance from a point, right? Same distance from a point, then that might map out a circle, okay? So we are going to do a couple of loci. All right, so let's start. First one, right? The first one, if I give you a complex number z minus some point c, and I ask to find the modulus of that, and it's equal to r, then what you have there will be a circle, right? This here will be a circle. So this is a circle of center, whatever C is, and radius. And radius r. All right. So let's say I gave you something like this. Suppose I said, well, find the locus of this and then and just catch it as well, right? Let's say I gave you z plus 2 plus 2i, right? And that was equal to 3. Suppose I gave you something like that. And I wanted you to describe the locus and just catch it as well, right? Here's what we could do, right? What we could do is we could put it into this form and work it out. Or we could do it the long way in case we forget it, right? So I'm going to show you the long way first. So remember, z is equal to x plus iy. So what we have here is the modulus of x plus iy plus 2 plus 2i is equal to 3, right? Let's separate up inside the modular sign there. We bring in the real part together and we bring in the imaginary part together, right? How do we find modulus? Remember, this is modulus, right? Modulus is the square root of x squared plus y squared. So we have x here and we have y here. X is the real part, y is the imaginary part. So now we have the square root of x plus 2 squared, a plus 2 squared is equal to 3. Square both sides, and you'll get x plus 2 squared plus y plus 2 squared is equal to 3 squared. Okay, and now we'll recognize that this is a circle with, did I spell width wrong? Yes. It's a circle with center minus 2 and radius 3. So if I do a little sketch, it will be right here, right? And you'll have a circle. Right, this is minus 2, right? And the radius is 3. That's it. That's the way you do locus, right? Of course, the shortened version, once you memorize it, is this modulus of z, right? You factor it out, this will be minus. So it will be minus 2i is equal to r, right? Is equal to 3. So if you look here, you'll get your c from there, minus 2, and you'll get your r from there. Right, so I just showed you the long and the short way. Right, copy it down, screenshot it, anything you want. Right, you could use any version you want, right? Once you can put it in the form z minus c, right, go right ahead and use the short version. But if you get in trouble, use the long version, right? Separate the real imaginary and use the formula. Good, anybody writing?
Yeah.
Yeah, writing, go ahead. So where did the I go? Right. So the, you don't need the I, because remember, if you have 2 plus 3i and I ask you to find the modulus, and you will write the square root of 2 squared plus 3 squared, you just take the real and the imaginary. Right here. So same thing here. We don't need the I. We're just taking the real part and the imaginary part. I'm gonna finish, right? All right, so let's try this one here. Let me try something simple. The modulus of z minus 2 plus 3i. Try that there. Long or short, anyone you want. Right? Any method you want. Should get the same thing, right? Describe it. When they say describe, that's where you tell them is a circle with center R, center C, and radius R. When they say sketch, you just do a quick little thing. I'm gonna finish, right? This is the last topic in complex numbers. What is the modulus? Oh, sorry, sorry, what? Let's make it equal to root 3. Thanks. Yeah, you all got it? All right, nice job, Kilon. Right, so the short version, z minus 2 minus 3i is equal to root 3. So right here, you will see the center, 2 minus 3, radius root 3. That's it. Okay, if you do the long way, anybody do the long way? Yeah. All right. It's important that you learn to do it the long way because I'm going to give you our next version here, and we will see what you come up with. Okay. All right. So if you do it the long way, you'll get. In this case, you don't have to. X plus iy minus 2 plus 3i is equal to root 3. So that'll be the square root of x squared. Sorry. That'll be the square root of x minus 2 squared, y plus 3 squared is root 3. So when you square both sides, you'll get x minus 2 squared, y plus 3 squared is 3. So again, you can see that the center here is 2 minus 3, radius is square root of 3. Okay, right. So sometimes it looks like that, and then sometimes you're going to get it looking like this, right? I want to see you try this one. So you're going to get the modulus of minus 2 minus 2i is equal to z plus z plus 3 minus I. Try that there for me, right? Try this one here. Take your time. Get this one. All right, so take your time and replace z, right? Z is x plus iy. Let's see what it simplifies to. Right, so you should have that form there. Simplify it out, square both sides, and then see what it turns out to be, right? For those who got it, message what you got. If you could, or you can send a picture. Nice. Right, Rana, you'll have to expand. Right, so after you square both sides, you're going to have to expand it out a little bit, right? Right, when you expand, it will simplify out nicely. So here you'll end up with the square root of x minus 2 squared plus y minus 2 squared, square root of x plus 3 squared, y minus 1 squared. Right, when you square both sides, you'll end up with x plus 2 squared, y minus 2 squared. Here you will get x plus 3 squared plus y minus 1 squared. Right, you're going to have to expand it off because things will cancel off, right? So you'll get x squared, x squared minus 4x plus 4 plus y squared minus y plus 4 is equal to x squared plus 6x plus 9 plus y squared minus 2y plus 1. Right, x squares will cancel with the y squareds, and then you'll end up with what here? You'll end up with minus 4x minus 4y plus 8 is equal to 6x minus 2y plus 10. Right? Bring the y's across, so that's minus 4y plus 2y, 6x plus 4x plus 10 minus 8. So I got minus 2y is equal to 10x plus 2. If you divide everything by minus 2, you'll get y is equal to minus 5x minus 1. You'll get minus 1 or plus 1? Minus 1, okay. Check back yours, Keelan. Let's check back the signs there and see. So basically, we got the equation of a line. So it's a line y is equal to minus 5x minus 1. Right, so you have to go all the way down and simplify it out to get the actual equation. So in this case, when you had the modulus on both sides, it wasn't a circle, it was a straight line. So to kind of reduce the amount of things you have to learn, once you could solve it, it's much easier to just do it that way. It might take you a little minute more, but it don't matter what you see in front of you. Once you can solve it, you can work it. It'll be easier for you. Right? Sometimes when you use the short version, you kind of read off sometimes you read off the points wrong. Right? And that's why you just have you'll lose some marks for that, of course. Okay, copy this one down, you expand it out. And when you simplify, you end up with a straight line. So you have to write a straight line with gradient. Well, you don't have to write that kind of straightforward. So just write the equation of a line. So your locus is the equation of a line. Y is minus 5x minus 1. Nice. Anybody writing? Right. Of course, if they ask you to sketch it, you just do a negative slope with a y-intercept of -1, right? If you had to sketch it as well. All right, everybody done, right? Try this one here for me, please. Same thing, 2 modulus, right? See what you get here. Nice. I see the equations coming in. All right, 2 minutes again, then you'll see what you have. Right, of course, you'll recognize here that you have no, it's only like 0, 2 you have there, right? For this part, there is no real part. Same thing here. So you're going to get the modulus of x plus iy plus 2i as the modulus of x plus iy minus I. So this will be the square root of x squared plus y plus 2 squared is the square root of x squared plus y minus 1 squared. Square both sides, you'll get x squared plus y squared plus 4y plus 4, x squared plus y squared minus 2y plus 1. X squared, y squared canceling off still. Nice. And you'll be left with 6y is equal to minus 3. Yeah, minus 3. So y is minus a half. Yeah. That could work. You'll get that. Minus half. Okay, yeah, seen some answers like that. Nice. Right, just check back your expansion. Probably not your expansion. Check back what you use under the square root sign there. Yeah, nice. All right, good. Any questions here? Are you okay with this one? Nabil, again, should I? Okay. All right. So I wanted to try this one here. Remember, modulus is the square root of the real squared plus the y plus the imaginary squared. If I give you argument now, remember argument is the square root, is tan inverse of imaginary over real. So I wanted to try this simple one here. I just want to see what you got. Let's say that the argument of z is pi on 4. Try to see if you could work out what I will give you. Of course, this one here was a straight line, right? Y is equal to negative a half. Yeah, anybody have anything? What's the argument of z is equal to pi on 4? What does that look like? All right, yeah, I just want to see a try. I just want to see a try. If you get a line or a curve, remember it's a locus you're trying to get, right? If it's a line or a curve or anybody else? All right, so let's see what you came up with. Let's see how we're doing this. Good job, Keelan. All right. So you have tan inverse. Oh, sorry, let me write one line before that. Argument of z is x plus I y is equal to pi on 4. And we know that argument is equal to tan inverse of the real, right? So tan inverse y on x is equal to pi on 4. But I'm not looking so nice, so let's move it tan. And we will get y on x tan pi on 4. If you go to calculators, you'll get tan pi on 4 is 1. So therefore, we're getting y is equal to x. So we get in a line, y is equal to x. Okay? Right, but we want to be a little specific with this line, which is here now. Here's the part that we need to get right. So if I were to draw this line, right, we all know what line the line y equal to x will look like. The line y equal to x will look like that. But here's the problem. The problem is the argument is pi on 4. So pi on 4, as far as we know, pi on 4 is here. Pi on 4. So what that means is that the only part of the line that is valid will be this part here. We're ignoring this part here. That part of the line is not valid because the argument for that part of the line will not be pi on 4. Right? Right? So y on x, sorry, y equal to x, the part that you're going to draw is the part from the part above the x-axis, right? And this that we have in front of us is called a half line. And the reason why it's a half line is because only half of the line is defined, right? Only half of the line is defined. So it's important when we do a sketch, let me say that's a sketch, we have to check out the argument, right? We have to check out the argument. If the argument is pi on something, we sketch it and we erase the next part of it. Okay, so in general, this is your rule here. In general.
So I'll stop copying.
Yeah, I'll turn back just now. So generally, the argument of z minus a is equal to some angle theta. This is a half line. This is a half line starting at A and making an angle theta with the positive x-axis. Right, again, right, same way we would draw argument, right? Is the last one that we have to do. Copy that down and then I'll go back and you could write down that next part there. I wanted to see how you would have handled it. That's why I gave you that first. So let's copy this down and then I'll go back and you'll write down the example that we did. Right, good. Going back to the example now. Finish?
Yes, sir.
All right, good. Let's try one now. That was general, right? All right, let us try one. Oh, this will be too technically, right? Let's try the argument of c plus 2 plus I is equal to, let's keep it simple, right? Let's do pi on, no, pi on 2, not really. Let's do 3/4 pi. Try that, please. All these are half lines, huh? All these are half lines, so don't draw the entire line. All right, so you should have something. Right, remember, if you put it in the form, this will be z. If you put it in the form, this will be z minus 2 minus 1i, right? The reason you need that is you need to know where to cut off from, right? So this is the argument of x plus iy plus 2 plus I is equal to 3 pi on 4. So this is the argument of x plus 2, y plus 1 by I is equal to 3/4 pi. So this is tan inverse y plus 1 over x plus 2 is equal to 3 pi on 4. So y plus 1 over x plus 2 is equal to tan 3/4 pi. What's that again? What's tan 3/4 pi? What you all got for tan? Minus 1. All right, thanks. Minus 1. Right, so you multiply it out, you'll get y plus 1 is equal to minus x minus 2 minus x minus 3. Right, so it's the equation of a line. You see in the y-intercept is a negative gradient, right? So it might look something like this, right? Minus, yeah, negative gradient. There's your y-intercept. Good. We need to know where to cut off, right? We need to know where to cut off, right? So the cutoff point, if you read it off from here, you need to read it off from here, that'll be minus 2 minus 1. Right, where is that? That's like somewhere here. Right, yeah, about there, right? Isn't 3/4 pi. Yeah. Right, so what are you gonna do, right? So 3/4 pi is right here. So we're cutting off all of this here. Okay. So it's a half line. It's a half line. If you have to describe it in words, it will be a half line starting at what we said, minus 2 minus 1. Right? Excluding that point. Yeah? So I should draw a hollow circle. It should be a hollow circle. Right? So it's a half line starting at minus 2 minus 1 with equation y is equal to minus x minus 3. Right? And you could also say at 3/4 pi on 4 to the x-axis. Right? So sketch the line, plot minus 2 minus 1, draw a hollow circle there. Right? Remember, hollow means that point not included, right? And then erase the part that you don't want. So what did you do to make, hold on, up on there, boy. What did you do to make the form to get minus 2 minus 1? Oh, I just put it in the form I gave you here. Z minus E. Put it in the form Z minus E. Right? So what I did here is I put it in the form Z minus E. And then when I got E, I read off the real and the imaginary there. Minus 2 minus 1. All right. So in the fourth line, Why isn't it pi plus tan inverse? Oh, no. You're not doing all that. That is when you're trying to get the argument. We already know the argument is 3/4 pi. So you're not using that third quadrant and fourth quadrant thing, no. You're just going straight to the calculator and working the value out. Right? We already know that is 3/4 pi. Okay, so to describe it, you will say it's a half line starting at -2, -1, right? With equation y is minus x minus 3. Once you give the equation, you don't really have to state the angle to the positive x-axis. You don't have to state that because only one line could do that for you, right? But if you look in textbooks, they might just have half line and the angle and the point where it's starting from, right? But I like to obtain the equation as well. So you can actually do the plot. Any other questions on that? Let's try one more now. Varun, Benicia, you all doing okay there? Okay, so let's try one more now. Let's try one more, and then theory-wise, that's it for theory, right? You don't have to do inequalities and all those things. These are the general forms that we need to know. All right, last one, and that's it. And then we could take a look at the couple past papers, and that's it for complex numbers. So it means that Monday now we can spend time on starting differentiation. So if you want to review anything, you could just review how to differentiate. Differentiation real easy. Probably the easiest topic in Unit 2. The real stuff is the integration. That's where it gets a little difficult, and that's where we'll start in September. Right, I will send you your time, but if I'm not mistaken, your time is the same as last year, Wednesday, as Unit 2, same time, 5 to half 6. And you have the same option, face-to-face and online. All right, try this last one here, please. Right, find the argument of z. I'm gonna use some plus. What I gave it as now, hold on, plus and plus, so let me give you some minus then. All right, -2 minus 3i is equal to pi on 6. Roseanne, who's Roseanne? All right, let's see what you got. So this is the argument of x plus iy, right? Remember, you'll need to get a. So z minus 2 plus 3i, right? So it means that the point that we starting at will be 2, 3. Right, so that'll be this minus 2 minus 3i is pi on 6. So that'll be tan inverse of y minus 3 over x minus 2 is pi on 6, right? So you'll get y on 3. What's tan pi on 6 again? So you'll get y minus 3 by x minus 2 is equal to tan pi on 6. Right, so that's 1 on root 3. So that's y minus 3 over x minus 2 is equal to 1 on root 3. Right, not looking too nice, but we'll get y minus 3 is equal to 1 on root 3 by x minus 2. So y is equal to 1 on root 3x plus, minus 2 on root 3 plus 3. So that's 1 on root 3x, that's a positive gradient. Right, what is 2 on root 3, minus plus 3. Right, I just wrong in the 12, so I'll know where to plot it. I got positive 1.84, right? So the line that have a positive y-intercept, I just drawing the whole line, right? Is a positive gradient, positive y-intercept. So I'm drawing the whole line for you first. This is the y-intercept. But remember, the half line will start at somewhere here, right? 2, 3. So you do want this part here, right? You draw your hollow circle here, and your angle is pi on 6. Right, so ignore this part of the line here. Right, if you want, you could expand it out. So that is your that's your locus. Half line starting at 2, 3, right? With the equation y is 1 on root 3x plus 1.84. Any questions there? Any questions, Olia? Right, did I send 20? No, I didn't send 2016. Anybody can send me 2016 there, please? Anybody can send 2016, please? Yeah, just send a copy of 2016 now. All right, nice. Okay, so that's the end of theory now for complex numbers. Let's try some questions. And then we're done. then we are finished. Right, we will do that. In fact, let's do the whole thing now. I sent in 2016 in the group. I wanted to try A and B. Right, A and B in 2016. Yeah, like a plot here. So I wanted to try from A straight to B. I'll share it in group here one time. Right, so just one quick reminder. Always remember, right? And we would have seen this in a couple examples. If one of the roots is 1 minus 3i, the next root is 1 plus 3i. Yeah? Don't forget that. Right? Every time we had solve a equation, remember, you always get like 3 plus or minus 4i or something. So they always exist in conjugate pairs. So in case you didn't pick that up, write that down now, please. The roots, right? The roots of a quadratic are always in conjugate pairs of each other. All right, so I sent in a group there. Try A from a part 1 and 2, and then try B. Okay. Right, that's 3 marks, 6 marks, that's 9, 10, 11, 12, that's 18. So you should take about 20 minutes or less in an exam to do this. All right, try it, please. I'll give it some time to try it out, right? A and B. All right, you're almost done. And just checking out the first two parts in the meantime, right? That should be fairly okay. Oh wait, I can't write. Right, can I write now? Right. So good. So we know alpha. Alpha is 1 minus 3i. So beta has to be 1 plus 3i. So therefore, alpha plus beta, that will be 2. Alpha by beta will be 1 squared plus 3 squared, 10. Okay, so we know alpha plus beta and alpha by beta. So we're good to go there. Next, find an equation whose roots, show that. So we need to get 1 on alpha minus 2 plus, right? Remember the usual thing, x squared minus the sum of the roots by x by the product is equal to 0. So you want to get the sum of the roots and the product of the roots. Right, so your LCM here will be alpha minus 2 beta. Numerator will be beta minus 2 plus alpha plus alpha minus 2. So underneath we'll get alpha beta minus 2 alpha plus beta plus 4. On top, we'll get alpha plus beta minus 4. So alpha plus beta was 2, so that's 2 minus 4 on top. 2 minus 4 on top, and underneath will be alpha by beta, which is 10 minus 2 by 2 plus 4. So that'll be minus 2 over 10. Anybody got that? Minus 1/5. So the sum of the roots. Anybody get that for the sum of the roots? Minus 1/5. Let's check and make sure I multiply right. All right, and then the multiplication will be 1 over whatever the denominator was, which was 10. So it's 1/10. So when you substitute it, you'll end up with x squared minus the sum, which is plus 1/5 x, plus the product, which is 1/10. Multiply everything by 10, you'll get 10x squared plus 2x plus 1. That's it, QED. And we show you there. It's closer to a unit 1 question as opposed to, but it's like Form 5 really. Hard math question. Right, copy down, screenshot. Let's take a look at the next part. Okay, nice. Next part. Right, on the Argonne diagram, they want you to plot complete U. So where is U? 4, 2. So that'll be like somewhere right here. Right, so that's where U is. That's the modulus of what? 16 plus 4 root 20. You can simplify root 20 if you want. So that'll be 2 root 5. What you all got for the quadrant, right? So the argument of U is tan inverse 214. How much is that? Oh, again, decimal. Right, I got 0.46. Right, first quadrant, right? Right, by the way, 3 is 2 root 5 is how much? 2 root 5 is about. And then they want you on the same Argonne diagram, sketch a circle. They say you already know it's a circle. Z minus U is equal to 3. So because we just finished loci, we know that the center is 4, 2, and the radius is 3. Right, so you want to try to sketch that here. Let me try and do it in blue. Center is 4, 2. Radius is about 3, right? So we do a little plot. We'll go up here, go across here about 3, come down here about 3, and here's about 3. Right, so it would be perfect, yeah, but we could get a circle that looks like this. Anybody reach all there and got that? Right, so the one in blue is the answer for part 2, where you do the sketch. You are okay with that? So we just do this sketch on top of the complex number there. Any questions on that? I'm not a little tired. We're almost done. Last thing. Next time, that's it. We are almost done. It's a couple of minutes again. Anybody reach there though and got that? All right, just do this last one here for man, we're done. Right, U over V to the power of 5. They want the modulus and the argument. As a little 6 marks there and we're done. U over V to the power of 5 and we're done. Try to use the rules, right? So it will help you out. All right. I want you all to try this out, right? So you have two ways you could do it. You could find U and V separately, right? Simplify U and V, realize it, simplify it out, and then find the modulus and argument. Or you could separate it up, find U5 and V5, and then work it out. All right. So looking like plenty of tired and you already reached here yet, right? So what I will do is I will stop here, try this out for homework. Next day, I will post a little solution on it, and we will start differentiation. All right. So I want you all to take some time, take a little break, come back, and just try it out. All right. You could try a couple other years if you want, and I could check it for you. Right. If you want to try the 20 and 21 and 22 and thing, you could try the complex in it. All right. So that's it for today, Olia. Right. We will stop on Monday. We will start differentiation and do a little quick solution on this. All right. So that's it there. All right. And all the time. So we will stop there. You all can log out, and I'll see you all Monday, please.
Bye, sir.
All right. Bye. Bye. It does. Chelsea, you good there?